Hi everyone. Today we discuss the one of the important topic is homomorphism, ring homomorphism. First we see the definition of ring homomorphism. A mapping phi from the ring R into R dash is said to be homomorphism if it satisfies the following two conditions. First one is phi of A plus B is equal to phi of A plus phi of B. The second condition, phi of AB is equal to phi of A into phi of B for all A comma B belongs to R. If phi from R to R dash is a homomorphism, phi of R is a homomorphic image of R under phi. Note, in the above condition, the operation plus and dot on the left side need not be a same. The plus and dot on right side. Since the left side operations are the operations of R and the right side operations are the operations of R dash. Endomorphism. Let R plus and dot be, that is the ring, phi of R to R is said to be endomorphism if first condition phi of A plus B is equal to phi of A plus phi of B. The second condition phi of AB is equal to phi of A into phi of B for all A comma belongs to R. Endomorphism is nothing but we are taking the mapping from R to R. A homomorphism from R into itself is called an endomorphism. Isomorphism of a ring. Let we consider an ring with operation plus and dot as well as R dash with plus and dot be any two rings, then a mapping phi from R to R dash is said to be an isomorphism from R into R dash if first condition is phi is homomorphism, that is phi of A plus B is equal to phi of A plus phi of B. Phi of AB is equal to phi of A into phi of B for all A comma B belongs to R. Second one, phi is 1 1. Third one is phi is onto. Automorphism. A, we consider an ring R. B, phi from R to R itself is said to be an automorphism if phi is homomorphism, that is phi of A plus B is equal to phi of A plus phi of B. Phi of AB is equal to phi of A into phi of B. Phi is 1 1 and phi is on R. Another definition is a 1 1 and onto homomorphism is called a automorphism. Remark, a 1 1 homomorphism is called monomorphism. A onto homomorphism is called epimorphism. Next we see the few problems regarding homomorphism. First one, prove that the transformation x plus iy implies x minus iy is an automorphism of the field of complex number. That is, definition, we are defining a map from C to C by f of x plus iy is equal to x minus iy, where x comma y belongs to R. Let a comma b belongs to C. That is, we are taking a is equal to x1 plus I y1 and b is equal to x2 plus I y2, where x1, x2, y1, y2 belongs to a real number. Therefore, f of a is equal to f of x1 plus I y1 is equal to x1 minus I y1. Similarly, f of b is equal to f of x2 plus I y2, that is x2 minus I y2. F is homomorphism, that is phi of a plus b is equal to f of x1 plus I y1 plus x2 plus I y2. That is nothing but next we separating real part and imaginary part, that is f of x1 plus x2 plus I into y1 plus y2. By the definition, this is nothing but x1 minus x2 minus I into y1 plus y2. Now, the above equation can be written as x1 minus I y1 plus x2 minus I y2, that is f of a plus f of b. Next, we are considering f of ab. F of ab is equal to f of x1 plus I y1 into x2 plus I y2. That is nothing but x1 x2 plus I y1 x1 y1 plus I into y1 x2 minus y1 y2. That is f of x1 x2 minus y1 y2 plus I into x1 y1 plus y1 x2. That is, we are take it as an x1 x2 minus y1 y2 minus I into y1 x1 y1 plus y1 x2, that is x1 minus I y2 into x2 minus I y2, that is f of a into f of b. Therefore, f of f is homomorphism. Now we are proving f is 1 function. To prove f is 1 function, we take f of a is equal to f of b, that is f of x1 plus I y1 is equal to f of x2 plus I y2. x1 minus I y1 is equal to x2 minus I y2. Now we are equating real part and imaginary part. Therefore, x1 is equal to x2 or y1 is equal to y2. A is equal to x1 plus I y1 can be written as a is equal to x2 plus I y2, because x1 is equal to x2 and y1 is equal to y2. Therefore, a is equal to b. F of a is equal to f of b. Now we prove f is 1. Now we are proving f is onto. The pre-image of x1 minus I y1 is x1 plus I y1. Therefore, f is onto. Thus, f is automorphism. Next problem is show that the correspondence m plus n root 8 minus m minus n root 8, where m and n are integers, is an automorphism of z of root 8. We are defining a mapping from f from z of root 8 into z of root 8. Let a is equal to m1 plus n root 8 and b is equal to m2 plus n2 root 8. F of a is equal to f of m1 plus n1 root 8 is equal to m1 minus n1 root 8. Similarly, f of b is equal to f of m2 plus n2 into root 8 is equal to m2 minus n2 root 8. This is by definition. Next, we proving f is homomorphism. Consider f of a plus b. That is, f of a plus b is nothing but m1 plus n1 root 8 plus m2 plus n2 root 8. And rearranging this term, we get f of m1 plus m2 minus n1 plus n2 into root 8. Now, we are applying the definition, we get m1 plus m2 minus n1 plus n2 root 8. Rearranging the term, we get m1 minus n1 root 8 plus m2 minus n2 root 8. That is f of a plus f of b. Next, we are taking f of ab. F of ab is equal to f of m1 plus n1 root 8 into m2 plus n2 root 8. Multiplying, we get f of m1 m2 plus 8 into n1 n2 plus n1 n2 plus n1 m2 into root 8. Now we are applying the definition. We get m1 m2 plus 8 into n1 n2 minus n1 n2 plus n1 m2 into root 8. In first we take m1 as common in first and third term. Therefore m1 into m2 minus n2 root 8, and we taking minus n1 in fourth term and second term. Therefore m2 minus n2 root 8. That is nothing but m1 minus n1 root 8 into m2 minus n2 root 8. Therefore f of ab is equal to f of a into f of b. Thus we prove that f is homomorphism. Now we are proving f is 1 1. F of a is equal to f of b. That is m1 minus n2 into root 8 is equal to n2 minus n2 root 8. Equating the corresponding term, we get m1 is equal to m2 and n1 is equal to n2. Therefore f is 1 1. Now we are proving f is onto. The pre-image of m1 plus n root 8 is m minus n root 8. Therefore f is onto. Therefore we prove that f is automorphism. The next problem is a mapping phi of x is equal to 2x for all x belongs to z. A homomorphism justifies by defining a map from z into 2z. That is f of x is equal to 2x for all x belongs to z. Let x comma y belongs to z implies x plus y belongs to z. Therefore, phi of x is equal to 2x, phi of y is equal to 2y, phi of x plus y is equal to 2 into x plus y. Consider f of x plus y is equal to 2 of x plus y, that is equal to 2x plus 2y. It satisfies the first condition of homomorphism. Next we are considering phi of xy is equal to 2xy, that is 2x into not equal to 2x into 2y. Therefore, phi of xy is not equal to phi of x into phi of y for all x comma y belongs to z. That is, it does not satisfy the second condition of homomorphism. Therefore, phi is not a homomorphism. Next problem is let R1 and R2 be two rings from R1 to R2 by f of x is equal to 0 for all x belongs to R1. Show that f is homomorphism. Let we are taking x comma y belongs to R1 implies x plus y belongs to R1 for all x comma y belongs to R1. F of x is equal to 0, f of y is equal to 0, f of x plus y is equal to 0. This is by given. Therefore, consider f of x plus y is equal to 0. 0 can be written as 0 plus 0. That is nothing but f of x plus f of y, which satisfies the first condition. The second condition is f of xy is equal to 0. Therefore, 0 into 0 is nothing but f of x into f of y. It satisfies the both condition of homomorphism. Therefore, f is homomorphism. Note R1 and R2 be two rings, then the mapping from f from R1 to R2 by f of x is equal to 0 for all x belongs to R1 is a homomorphism. This homomorphism is called zero homomorphism or trivial homomorphism. Now we see the few properties or theorems on homomorphism. Under any homomorphism, zero elements are mapping to zero element. Or if f from R to R dash is a homomorphism of ring R and R dash, then f of 0 is equal to 0 dash, where 0 and 0 dash are zero elements of R and R dash respectively. Let R from R dash be a homomorphism of two ring R and R dash. Let 0 and 0 dash be the elements of R and R dash respectively. We know that 0 plus a plus 0 is equal to a. Therefore, f of a plus 0 is equal to f of a. F of a plus f of 0 is equal to f of a. F is a homomorphism. F of a plus f of 0 is equal to f of a plus 0 dash. By left cancellations law, f of 0 is equal to 0 dash. Therefore, under any homomorphism, 0 elements are mapped to 0. Next theorem, under any homomorphism, additive inverse or mapping to additive inverse, or the same statement can be say that if f from R to R dash is a homomorphism of ring R and R dash, then f of a is equal to minus a for all a belongs to R. Let, we proving this property, let f from R to R dash be a homomorphism of two rings R and R dash respectively. We know that a plus minus a is equal to 0 for all a belongs to R. Therefore, f of a plus minus a is equal to f of 0. F of a plus f of minus a is equal to 0 dash. F is homomorphism. Therefore, f of a plus f of minus a is equal to f of a minus f of a. That is, f of minus a is equal to minus f of a by left cancellation law. Therefore, under any homomorphism, additive inverse are mapped to additive inverse. Next theorem, f from R to R dash is a homomorphism of rings R and R dash. Then f of a minus b is equal to f of a minus f of b for all a comma b belongs to R. Or the above statement can be restated that homomorphism preserves difference. Let R and R dash be a homomorphism of two rings R and R dash. Consider f of a minus b is equal to f of a plus minus b. That is equal to f of a plus f of minus b. And f of a plus minus of f of b. That is f of a minus f of b for all a comma b belongs to R. Thank you.